If you've ever found yourself, walking up a ramp or navigating a really crowded stairwell,
Mm-hmm.
or maybe just noticing the distance between your hotel room and the fire escape,
Yeah.
you were interacting with a code.
Right.
A code so detailed it dictates the very DNA of modern architecture.
Yeah.
This isn't just some list of rules. It's a sophisticated, layered defense system baked right into our environment.
It's so true. We completely take for granted this invisible structure that's protecting us. But fire safety, I mean, it goes so far beyond basic smoke alarms.
All way beyond.
What we're diving into today is the absolute backbone of building security. The Code of Practice for Fire Safety in Buildings 2011.
And this is the brand new one.
The brand new one, just updated to its 2024 edition. It incorporates amendments right up through this past September.
And the weight behind this document is,
Yeah.
it's incredible. I mean, this code wasn't just pulled out of thin air, was it?
Not at all. It was prepared by the Buildings Department, and it's based on this enormous consultancy study. A leading firm, Ova Partners Hong Kong Ltd., did the work.
And look at who supervised it. A steering committee that brought together, well, everyone. Chief building surveyors, deputy chief fire officers.
Professors from major technical universities.
Right, HK Polytechnic University and HK West. Plus, representatives from every professional, body architects, engineers, surveyors. The works.
That multidisciplinary approach is absolutely essential. I mean, think about it. Fire safety is where structural engineering meets human psychology.
Yeah.
It's where chemistry meets logistics. And because it's so complex, the code doesn't just, rely on local wisdom. It adopts a hierarchical, performance-based regulatory system.
Modeled after some of the big ones, right?
Exactly. Highly respected codes in Australia, the USA, and New Zealand. It's best practice.
Okay, let's unpack this foundational framework because it really determines how every single design decision gets made. It's structured like a pyramid, right?
Precisely. At the very, very top is the overarching goal. This is set out by the building's ordinance itself.
A big law.
The big law. And it's simple: to ensure the planning, design, and construction of buildings, and critically, to render unsafe existing buildings safe. That's the long-term, non-negotiable objective.
And just below that, we have the functional statements.
Yes, these are the detailed what and why of fire safety design. They translate that high-level goal into specific outcomes.
I'd book, for example.
Like ensuring life safety is met through adequate means of escape, or guaranteeing that the construction itself inhibits fire spread. These are, well, they're the promises the building has to keep.
And this is where the two compliance paths emerge, defining how an architect or an engineer chooses to meet those promises.
Correct. So path number one is the path of reliability, the deemed to comply provision.
The rule book.
It's the rule book. These are the prescriptive rules laid out in the code. If you follow these specific measured rules, the required widths, the specified materials, the fixed distances, then your design is deemed to comply in a reliable way. It's the standard blueprint.
But what if a building is unique? Say, an exceptionally large airport terminal or a geometrically complex museum. The blueprint might not fit.
And that's when you pivot to the second path, the alternative solution, which uses the fire engineering approach.
Okay.
This requires you to apply rigorous scientific modeling and engineering principles to prove, beyond a doubt, that your unique solution still meets those core functional statements and performance requirements.
So it gives you flexibility.
It offers flexibility without compromising the safety objective. Yeah.
That makes perfect sense. It's a mechanism to handle both the predictable and the complex. Okay, let's unpack this, starting with the core philosophy that defines what a building is actually trying to protect.
The primary objective, and it's stated right in Clause A2.2, is unequivocally life safety.
That's the mission.
That is the mission,
Yeah.
ensuring all occupants can safely escape. If you look at the structure of the code, every single dimension and every rating feeds back into maximizing that outcome.
But the commentary reminds us that while life safety is, paramount, fire safety design is a holistic discipline. So what are the secondary objectives that still have to be considered?
They are critical supporting objectives. Things like preventing the outbreak of fire in the first place, actively abating existing hazards, improving fire suppression capabilities, and, yes, preventing excessive property loss.
So it's not just about people.
Well, this specific code focuses on the structural and evacuation elements, but you see the reflection of these other goals in other associated regulations like those governing fire service installations and, say, chemical storage.
Now, let's revisit the two compliance pathways, because they represent two fundamentally different ways of thinking about risk. The deemed to comply path is the workhorse.
It is the standard. It provides certainty for designers and for regulators. By following the prescriptive rules like mandating a specific fire resistance rating for a wall based on the building's use, you inherently meet the performance goals.
But that certainty comes with limitations.
It does, and this brings us to it's a shocking caveat really, in clause A6.1, which is often overlooked. It explicitly defines the boundaries of the standard prescriptive code.
What does it say?
This is the moment where the prescriptive code basically waves a white flag. It states plainly that the deemed to comply provisions have not taken into account scenarios involving significant and organized arson, terrorism, or similar major emergencies.
Wow. Okay, so the standard office building, the standard apartment block, it's built to handle an accidental electrical fire.
Right.
Or maybe even a localized small act of malice, but not a large-scale coordinated attack designed to overwhelm the building's systems.
Exactly.
Why can't the prescriptive code handle that?
Because the prescriptive code assumes a predictable set of variables, particularly the fire growth rate and the occupant's pre-movement time, the time they take to react. Organized arson or a terrorist attack fundamentally subverts both of those assumptions. They introduce, unusual fuel loads, complex ignition points, or systems designed to delay or confuse evacuation.
So you can't use the rule book for that.
You can't. To mitigate those specific risks, you must use the alternative solution fire engineering, which involves modeling that specific worst-case scenario.
That's a crucial insight for anyone relying on these structures. We're relying on continuous maintenance and human vigilance for everything outside of predictable accidental risk.
Absolutely. The level of safety against a catastrophic, willful failure is dependent on an individual, performance-based assessment. Now, when we talk about that performance, we need to detail what exactly the design must achieve.
Right.
The code sets out the mandatory performance requirements.
We mentioned the escape elements, the means of escape, which is B1 to B5. What specifically must the construction guarantee here?
Okay, so B1 requires adequate means for all occupants to evacuate safely. B2 requires protection from the fire's impact during that evacuation.
So you don't get burned on the way out.
Right. B3 demands adequate lighting and clear signage. In short, the escape route has to be usable and visible for the full duration of the evacuation.
And then there's the passive component. Fire-resistant construction, C1 and C2.
C1 is all about containment. It requires inhibiting fire spread not just internally, but between buildings to prevent a total conflagration.
Right.
It also demands that the structure facilitate fire service intervention, meaning the firefighters must have a stable, protected environment to operate within.
And C2?
C2 then focuses on the structural integrity itself. The building has to maintain its stability long enough for evacuation and intervention to conclude safely.
And finally, there's the management overlay, performance requirement F1. This acknowledges that the best physical design is useless if the system is just neglected.
F1 is the check on the real world. It mandates that all fire safety provisions, these complex passive and active systems we're discussing, must be kept in good working order for the entire life of the building.
And it goes beyond just the hardware.
Oh, yes. Furthermore, any necessary evacuation procedures must be effectively implemented. The regulation acknowledges that maintenance is a non-negotiable part of the safety framework.
Okay, moving from that broad philosophy to the specific application. The entire calculation of a building's safety infrastructure. It begins and ends with the occupants. It's the human factor that drives the design.
Precisely. The code's 8 major use classifications in Table A1 are the bedrock of the whole system.
So everything flows from this classification?
Everything. They're designed around a hierarchy of risk based on 2 things: the fire hazard of the building's contents and the characteristics of the people inside. Are they familiar, awake, mobile, dependent?
Let's start with the difference between classification 1, which is residential, and 2, transient accommodation. They both involve people sleeping, which is inherently risky, but the context changes everything.
It does. Residential occupants in standard flats, they're familiar with the layout. They know exactly where the exits are.
Right.
The risk is that they're asleep, which increases their initial response time. The code even differentiates this further, recognizing the higher density and complexity of, say, older tenement houses within this class.
But then classification 2, transient accommodation hotels, guest houses, that adds unfamiliarity to the sleeping element.
And that is a critical multiplier. Waking up in an unfamiliar environment dramatically increases the pre-movement time.
The hesitation time.
Yeah, because people often hesitate, they search for clarity, they might even move in the wrong direction before locating the exit. The design for a hotel has to compensate for this necessary time lag.
Then there's the heartbreaking risk of classification 3, institutional, where assistance is required.
This covers hospitals, nursing homes, and childcare facilities. That's 3A. Evacuation here isn't rapid self-preservation. It's resource-intensive movement requiring staff assistance because of the occupant's physical inability.
And 3B.
In 3B detention or correctional centers, the issue is the opposite. Evacuation is deliberately controlled and slowed by management due to security constraints. The safety plan relies less on individual speed and more on controlled, managed movement.
Classification 4, commercial, is split into familiar, which is business 4A, and potentially unfamiliar or high hazard, which is mercantile 4B.
Right. Offices, or 4A, are generally lower risk because occupants are awake, they're mobile, and they're familiar.
But mercantile, 4B retail, restaurants, bars, that's where the risk really accelerates.
It does. You have high occupant turnover, potential crowding, and critically, a high volume of potentially flammable goods, the merchandise, which significantly raises the fire growth rate.
And classification 5 assembly is purely about crowd size and potential confusion.
Yes. Large groups for entertainment or deliberation. This class is finely subdivided from cinemas and theaters 5A to educational facilities 5B, and then to general assembly 5PIN.
Which includes what?
Venues like arcades or columbaria. The commentary points out a unique psychological risk in places like arcades. The occupants might be so engrossed that they temporarily lose the capacity to rapidly identify and respond to an emergency.
Wow.
The design has to overcome that sensory distraction.
Finally, industrial, which is 6, car parks 7, and plant rooms 8. Here, the risk is mostly about the stuff inside.
Exactly. These are defined by the sheer fuel load or the hazardous nature of the contents. Industrial facilities range all the way up to 6C, which is for storing hazardous goods. Those premises face extreme fire risk and consequently have the most restrictive volume limits and highest FRR requirements to prevent catastrophe.
The use classification then instantly dictates the required exit capacity via the occupant capacity metrics in Table B1. This is where the engineering assumptions about human density get really fascinating.
This table calculates the total capacity by defining how many square meters of usable floor area are allocated per person. The differences really illustrate the lost perception of risk and crowding.
Let's look at that scale. What is the safest, least dense assumption made in the code?
The lowest density is assigned to warehouses, car parks, and plant rooms. Uses 6B, 7, and 8. These require a massive 30 square meters of floor area per person.
30.
Yeah. This assumes very low staffing relative to the volume of the space.
And now the extreme opposite. Where is the highest assumed density? Where does the code expect a crush of people?
If you are designing a betting hall, a banking hall, or an open viewing gallery, the capacity factor drops to just 0.5 square meters per person.
Half a square meter.
Half a square meter. Think about that.
Right.
You have to design for 60 times the density of a warehouse. It's an enormous design constraint that mandates extremely robust and numerous escape routes. For comparison, restaurants, bars, and pubs are set at 1 square meter per person.
So it's the law anticipating the absolute worst-case scenario for human compression.
Absolutely. And while these density factors are used for design, the building authority reserves the right to use actual counting as the most reliable way to establish maximum capacity.
So they can come in and just count heads.
Yes. If a building is operating far denser than the design assumptions, the authority can step in to enforce limits based on actual observation, overriding that initial square meter calculation.
Once that maximum occupant load is fixed, the process becomes, well, pure prescriptive geometry, Part B, means of escape. These are the mandatory dimensions that maximize flow and minimize panic.
Indeed. We should first note the few buildings that are excluded. Small, single-family domestic buildings. Not more than 3 stories, highest floor less than 13 meters above the ground.
But anything larger than that
Must conform to these very strict rules.
Let's start with the required exits and width in Table B2. It seems self-evident, but the minimum widths are all about maximizing throughput under stress.
They ensure the flow rate. Up to 30 people, you need 1 exit, but even that single door has to be at least 750 millimeters wide, with the route itself 1050 millimeters wide.
Okay.
But once you hit 31 to 200 people, you jump to 2 exits minimum and a total aggregate door width of 1750 millimeter. This is all about redundancy and capacity.
And that minimum width continues to climb, ensuring that a single person isn't solely responsible for the width calculation.
Right. By the time you reach 501 to 750 people, 3 exits are mandatory, and each of those exits must be a substantial 1,200 millimeters wide.
And for the really big crowds.
For the largest crowds like exhibition spaces that might hold over 3,000 people, the code's commentary strongly suggests you leave the prescriptive rules entirely and move into specialized fire engineering analysis because standard dimensions just won't cut it.
Next up, travel distance limits, B11.2 and B11.3. This is the measure of urgency built into the design. How fast do people need to reach safety?
Travel distance defines the maximum time the occupant is exposed to the fire. In standard internal corridors for most uses, you have a maximum of 18 meters to reach a point of choice.
What's a point of choice?
It's a position where you can choose between 2 separate escape routes. From that point, the maximum total distance to the nearest protected exit is 36 meters.
And the separation of those 2 routes has to be definitive, not just a slight jog.
Correct. B11.7 requires that the lines drawn from that point of choice to the 2 exits must form an angle of at least 30 degrees. This is to prevent both routes from being compromised by a single, localized event.
We mentioned the balcony approach earlier. The external corridor are often seen in residential and hotel designs. Why does that allow for longer travel distances?
Because the risk of smoke logging in high temperature is significantly reduced when the corridor is external and naturally ventilated.
Right.
For residential and transient uses, the distance from the unit door to the staircase is limited to 24 meters internally. But if a balcony approach is used, the total distance can safely stretch out to 45 meters. The engineering premise is that the open air buys you time.
Let's move to the geometry of escape. The staircase requirements in B14. Why such obsessive detail on the height and width of every single step?
This is fundamental human ergonomics under stress. The stairs must be straight flights, no dangerous winder.
I hate winders.
Everyone does. To maintain flow and prevent tripping, you are limited to a maximum of 16 risers per flight and a minimum of 2. Crucially, the standard tread depth is 225 millimeter minimum, and the riser height is 175 millimeter maximum. These dimensions are designed to maintain an even, quick descent under panic.
But those dimensions change based on the assumed vulnerability of the occupants, right?
Yes. If you look at high-density assembly uses like cinemas and theaters, 5A, where people might be moving in low light or in large crowds, the safety factor increases.
How so?
Treads must be wider, a minimum of 280 millimeters, and the risers must be shallower, a maximum of 150 millimeter. This reduces the likelihood of falls that could create a mass pileup on the staircase.
And the maximum width rule is a bit counterintuitive. You can't just build a 10-meter wide staircase. Why the 1,800 millimeter limit?
A required staircase cannot exceed 1,800 millimeters unless it is divided by a central handrail into separate bounded sections. This is a crowd control mechanism. Extremely wide staircases encourage disorganized lateral movement and competitive descent, which reduces overall flow efficiency and increases crushing risk. By compartmentalizing the flow into these 1,050 millimeter to 1,800 millimeter sections, you maintain order and efficiency.
Finally, the last chance before safety. The doors, B13. What are the critical functional requirements here?
Flow, flow, flow. Any door serving an occupancy load over 30 people has to open in the direction of exit.
The classic anti-crush rule.
Exactly. If 31 people are trying to get through a door that opens inward, the crowd pressure will just jam it shut.
And the fail-safe mechanisms for security are fascinating.
They have to be. If the door is locked from the outside for security, it must be instantly openable from the inside without a key. More technically, if electronic locks are used, they have to automatically release upon the fire alarm signal actuation, and they must release upon power failure. That ensures that if the fire takes out the electricity or the data cables, the system defaults to the open position, ensuring immediate egress.
So Part B gets the people out, and Part C keeps the fire contained while they are moving. This is the realm of passive measures, fire resistance rating, or FRR, which measures how long a structure can stand against the heat and flames.
FRR is the time bomb built into the structure. It's defined by 3 criteria. Stability, will it stand? Integrity, will it crack or let flames through? And insulation, will the unexposed side stay cool?
And these fire barriers create compartments.
Essential for slowing the spread.
How does the used classification translate into the required FRR, according to Table C1?
For most standard uses, residential, transient, and smaller commercial facilities up to 2,500 square meters, a 60-minute FRR is the baseline. This is seen as the minimum time needed to ensure total evacuation and initial fire service setup.
But the riskier and larger the facility, the higher that rating climbs.
Yes. Large commercial or mercantile facilities over 2,500 square meters and most high-hazard industrial uses jump to 120 minutes.
2 hours.
2 hours. This rating reflects both the larger area the fire can spread in and the higher fuel load. We see this acutely in industrial storage, warehouses 6B, where the volume is capped at 28,000 cubic meters, and hazardous goods storage 6C, which is capped severely at only 7,000 cubic meters. Both require 120 minutes of resistance. The volume limit is the ultimate control factor for the fuel load.
The integrity of that compartment relies entirely on how penetrations are handled, which is C8. A concrete wall is useless if the pipes running through it aren't protected.
Absolutely. Openings and fire barriers have to maintain the full required FRR of the surrounding wall or floor. This means fire-rated doors, shutters, and crucial details like fire dampers and ductwork and fire-stop material sealing cable or pipe penetrations.
There's a vital and I think often missed element, especially for residential safety, protection against smoke spread.
This is addressed specifically in Clause C6.1 regarding flats or guest rooms that lead to common internal corridors. Every fire-rated door serving these units must be equipped with a smoke seal.
And the code is clear on this.
Very explicit. The code commentary says a tight-fitting and latched fire-rated door alone does not prevent smoke spread. Smoke, driven by pressure and convection, will find the tiniest gaps. The seal is essential because smoke is the primary hazard to life safety.
Buildings also have to protect themselves and their neighbors from external spread, like fire leaping from one window to the next. C5 and C11.
C5 addresses horizontal spread between buildings. If buildings are close within 1.8 meters, their external walls must be imperforate fire barriers.
Meaning no openings.
No openings. For vertical spread, C11 requires a separation between adjacent floors. This is typically achieved by a vertical spandrel, a solid wall section of 900 millimeters, or a 500 millimeter horizontal projection, like a balcony slab, both having adequate FRR.
But is a 900 millimeter spandrel really enough to stop the flame?
The commentary provides the honest answer. It only slows the flame spread. It buys time, but it doesn't guarantee containment. The most effective control against vertical fire spread, especially in high-rise structures, is a properly designed sprinkler system.
We also have to consider the special hazard areas. The engine room of the building like generator rooms and transformer rooms. That's C13.
These rooms are extremely fire-prone and have to be rigorously separated from the rest of the structure by walls having a minimum FRR of -120, 120.
But there's an even higher level of protection.
Yes, and here's the extreme level. If that special hazard area connects directly to a protected exit, like a staircase or a fireman's lift lobby, the separation rating must be enhanced to an incredible -240, 240.
4 hours.
4 hours. That rating is necessary because compromising the main escape route with a fire from a high-hazard area is completely unacceptable.
So a contained fire and efficient evacuation are critical, but the fire services department has to be able to reach the scene. That's where the emergency vehicular access, or EVA, comes in. That's D22.
EVA is the mandatory life support artery for the building. It has to accommodate the massive vehicles required for modern firefighting. The code specifies that the EVA must support a vehicle with a gross weight of 30,000 kilograms, a 12-meter length, and a huge 26-meter turning circle.
Just to get the truck in?
Just to get the truck in and maneuver. This ensures that the heaviest equipment can be quickly and safely deployed.
And the geometry of the access point is tightly controlled for that maneuverability.
On virgin sites, the carriageway has to be 7.3 meters wide, or 6 meters if it's hard paved. Headroom must be a clear 4.5 meters. Critically, the gradient is usually limited to 1.0. This low gradient is vital for ensuring heavy, fully loaded fire appliances can maintain speed and control.
The EVA also has to physically serve the building, meaning it can't just run parallel to a small section.
No. It must serve at least one major facade, which is defined as 1/4 of the total perimeter length, and the access must be within a horizontal distance of 10 meters from that facade.
That's interesting.
It is. And once the facade exceeds 60 meters in height, that 10-meter rule is sometimes waived, acknowledging that above that height, access is primarily internal via specialized systems.
Is EVA mandatory everywhere, or can a developer request an exemption due to site difficulty?
Exemptions are possible, typically for low fire risk buildings or where severe topographical constraints like very steep terrain make the access impossible. But this requires a comprehensive fire safety assessment report, an FSR.
And there's a trade-off.
Always a trade-off. If external access is compromised, the building authority will mandate compensatory enhanced fire safety provisions inside the structure to maintain the overall safety level. Safety can't be sacrificed just because the site is difficult.
Now let's talk about the internal high-rise systems. The firefighting and rescue stairways, D14 to D17. These are complex because they have dual purposes.
They combine a protected staircase for occupant escape and a specialized fireman's lift for fire service personnel, all within a highly protected enclosure.
And they have to be easy to find.
Yes. They must be easily accessible from the ground-level fire service access point within 18 meters horizontally.
And access to these critical stairways has to be managed through a highly protected lobby.
The lobby acts as an airlock. It must be separated from the floor area by fire and smoke-resistant construction, and it's sized specifically between 5 and 10 square meters to prevent congestion without encouraging lingering.
Right.
Critically, these lobbies generally require natural ventilation openings making up at least 25% of the floor area to ensure the space remains relatively smoke-free for firefighters and evacuees.
Now let's look at the true skyscraper element. Refuge floors, B18. These are absolute lifelines in buildings that exceed 25 stories.
They are intermediate, secure havens. They're mandated every 25 stories for most uses, or every 20 stories for high-risk industrial classifications. Their primary purpose is to provide a break for occupants descending the staircases and to compartmentalize the building against vertical fire spread.
And the rule is that these floors cannot be used for any revenue-generating or occupied accommodation.
Correct. They are strictly protected spaces, though essential plant rooms and water tanks are permitted. The net area for refuge must be at least 50% of the gross floor area, with a minimum clear headroom of 2,300 millimeter.
And they need to be open.
The design must ensure they are open-sided above a safe parapet on at least 2 opposite sides to guarantee cross-ventilation and smoke dissipation.
And there's a fascinating, almost counterintuitive design requirement about the staircase at the refuge level.
This is the mandatory diversion. Any required staircase passing through a refuge floor has to be discontinued at that level.
Why?
It forces occupants to cross the open refuge area before locating the continuation staircase downwards. This prevents 2 critical failures. 1, it prevents the staircase shaft from acting as a continuous chimney for smoke.
Oh.
And 2, it ensures that the physical act of crossing the floor breaks up congestion, preventing a massive blockage in the stairwell itself.
What about modern architectural features like communal sky gardens being incorporated into these refuge floors?
The code commentary advises that if communal sky gardens are included, elements like planters, equipment, and furniture, they don't count toward that mandatory 50% net refuge area.
Right.
Furthermore, to maintain the floor's integrity as a safe haven, the lift doors, other than the fireman's lift, have to automatically lock upon fire alarm actuation, ensuring that non-evacuating occupants don't clog up the space.
Okay, so we now move to the ultimate conceptual counterpoint to prescriptive rules, the alternative solution, or fire engineering approach in Part G. When the rules are too complicated or the structure is too unique, this is the pathway to compliance.
This is where science replaces simple rules of thumb. Fire engineering is used when prescriptive rules create genuine difficulty, often in highly complex or extremely tall buildings. The mandate is clear. You must demonstrate an equivalent overall level of safety to what the prescriptive code would have provided.
You're proving the outcome mathematically.
You are. And the core concept of that mathematical proof is the timeline method, RSET versus ASSET. This is the cornerstone of life safety assessment in fire engineering.
RSET versus ASSET.
Yes. It's a simple concept with profound implications. RSET is the required safe egress time, the total time it takes for every single occupant to reach a safe place. This includes detection time, pre-movement delay, and the actual movement time.
And ASSET.
ASSET is the available safe egress time, the time until conditions within the compartment become officially untenable, meaning too smoky, too hot, or too toxic.
So one has to be shorter than the other.
Dramatically shorter. The entire engineering goal is to ensure that RSET is demonstrably shorter than ASSET. The margin between the two is your engineered safety factor.
To calculate RSET and ASSET accurately, engineers have to analyze the building through 6 interconnected fire safety subsystems. G5, right?
Yep.
They can't just look at one element.
That's right. The safety of a complex building is defined by the interaction of these 6 systems. You have fire initiation and development.
So how a fire starts and grows.
Exactly. Then smoke development, spread, and control. Then fire detection, warning, and suppression, the active systems. Fourth is fire spread, impact, and control, which is the passive systems. Fifth is occupant characteristics and evacuation,
The people.
the people. And sixth is fire service intervention. How quickly can they get in and help?
The first step in calculating ASET is defining the design fire, the theoretical blaze the building must survive. How do engineers model that fire?
The design fire acts as the stress test. It's defined by the heat release rate, or HRR, over time. It traces the incipient, growth, flashover, fully developed, and decay phases. The crucial aspect here is the growth phase, which is typically modeled using the $2 or T-squared concept.
Can you break down the T-squared concept for us?
In plain terms, $2 means the heat release rate of the fire grows exponentially.
So it's a curve, not a straight line.
Exactly. By classifying the fuel load as slow, medium fast, or ultra fast, the engineer defines the steepness of that growth curve. A residential fire is usually considered medium growth, meaning it reaches peak heat relatively quickly, demanding a swift evacuation.
And we get insights into how complex these assumptions are, especially with the commentary on car parks.
This is highly instructive. Table G1 notes that for car parks, even with sprinklers present, the fire size may be modeled as similar to free burning.
Why is that?
Because the vehicle's canopy can actually shield the sprinkler water, making the suppression system potentially less effective at the point of ignition. This forces the engineer to model a larger, faster-growing fire scenario than you might expect, just to maintain that necessary safety factor.
Subsystem 5 focuses on the RSET calculation, and this is where human behavior becomes single biggest variable: pre-movement time.
This is the time between the warning being clearly received and the occupants actually deciding to start moving. It is the human bottleneck.
And it varies wildly.
Oh, Table G2 shows the vast, terrifying difference this makes. An awake, familiar office worker might have a pre-movement time of, say, 0.2 to 2 minutes. They hear the alarm, grab their bag, and go.
But a sleeping hotel guest,
Someone asleep in transient accommodation has a pre-movement time that can easily exceed 10 minutes or potentially over 50 minutes, depending on the reliability of the alarm and the training of the staff.
let's stop there and look at the profound implication of that. If a person takes 50 minutes just to get out of bed and locate the exit, the building's passive structure, the walls, the floors, the stairs, must maintain its integrity, insulation, and stability for that entire duration
Yes.
before that person even hits the escape road. The RSET calculation directly defines the required structural endurance, the ASET.
Exactly. The passive safety is directly tied to the longest possible delay induced by human inertia. That's why the structure matters so much in a residential or hotel design.
Once RSET and ASET are justified, the engineer needs objective limits to define the safe environment, or tenability. What are the specific scientific thresholds for an area to be considered safe for human life?
The acceptance criteria are very strict, and they're based on maintaining basic life support and visibility. First, smoke layer height. The standard adopted is 2 meters above the floor. This is the smoke-free zone. If the smoke layer stays above that, visibility for escape is maintained.
What about temperature?
If smoke does drop below 2 meters, its temperature must not exceed $60, and radiated heat transfer from the smoke layer above can't exceed $2.05 texapical limit down. This prevents thermal injury during escape.
And toxicity and visibility.
The key metric is carbon monoxide CO concentration, which can exceed the $1,000 Vesprom. For visibility, the optical density shouldn't exceed 0.1, which equates to roughly 10 meters of visibility. If the model proves these conditions hold until the last person is out, the design is compliant.
We've covered design, engineering, and architecture, but all of that effort becomes academic if the building isn't managed correctly. Part F addresses fire safety management, making it clear that continuous maintenance is mandatory.
The code commentary drives this home. The design is only as effective as its operation. This requires a fusion of legal compliance, not just with the buildings ordinance, but also with fire services ordinances and occupational safety and health regulations.
And the most basic, persistent hazard involves just blocking the means of escape. What are the legal ramifications for this simple act of negligence?
Under the fire services regulation, blocking or locking any means of escape is a criminal offense. This includes locking gates or placing obstructions in common staircases, even up to the roof level. The rule is that these paths must be readily and conveniently openable from the inside without a key at all times.
Maintenance isn't just about testing sprinklers, the active systems. Passive elements, the walls, the doors, they need continuous vigilance.
Yes. Fire doors, fire barriers, and emergency lighting must be regularly inspected. Fire doors, specifically, must be free from obstruction and kept closed if they are fire-rated. If any passive element needs to be temporarily removed for repair, alternative temporary safety measures, often temporary fire-rated hoarding, must be put in place to maintain the required safety standard.
A surprising amount of detail is dedicated to maintenance procedures for lifts, given the inherent risk of an open shaft.
Well, lift wells breach every single floor compartment, making them potential vertical pathways for fire and smoke.
Right.
So to prevent this during maintenance, only one landing door per lift well should be open at any time. If more than one door has to be removed, up to a maximum of 3 doors, no hot works like welding are allowed. And if more than one door is removed, temporary hoarding with an FRR of not less than -120 must be installed.
That 2-hour temporary barrier reflects the seriousness of opening that vertical chimney.
It does.
Let's discuss training, which is essential for managing the human factor delays we saw in the RSET calculations.
Staff training must ensure familiarity with exit routes and equipment, but the evacuation strategy for persons with a disability is paramount. The code also specifically addresses the danger of refuge floors.
How so?
Occupants must be trained not to treat the refuge floor as the final destination.
Because they might stop there thinking they're safe and cause a bottleneck.
Exactly. If people perceive the refuge floor as the ultimate safety point, they will congregate and potentially block the route. Training, guided by fire wardens, must ensure continued movement downwards until the ground level is reached or until fire services arrive.
And that leads directly to the mandatory provisions for persons with a disability. Temporary refuge spaces.
These are crucial elements required in the protected exit or fireman's lift lobby of every applicable fire compartment. They must be located no more than 60 meters from any point on the floor. The space must be at least 1.5 by 1.5 meters, large enough for a wheelchair to maneuver, and clearly demarcated.
And what technology is required to guarantee rescue from these spaces?
Each temporary refuge space requires 2 communication systems, both backed up by an emergency power supply for at least 1 hour.
Okay.
A closed-circuit television, or CCTV, link, and a direct intercom link to the management office or the fire services control panel. This combination ensures that management not only knows where the occupant is, but can also visually assess their condition, ensuring a prompt and targeted rescue.
This whole deep dive has shown that fire safety is achieved through an interconnected network of prescriptive architecture, complex performance engineering, human behavior modeling, and, well, continuous vigilance. It's a system designed not just to contain a fire, but to buy those crucial calculated minutes for life safety.
It is a phenomenal feat of systems thinking. We've seen the sheer complexity required to design for everything from a low-density warehouse to a high-density betting hall, all while balancing predictable rules against the need for advanced scientific modeling when those rules break down. The safety we rely on is measured down to the millimeter of a riser and the millisecond of human reaction time.
We learned that the standard prescriptive rules are simply not designed to withstand organized, premeditated failure like arson or terrorism, requiring a costly, individualized, performance-based solution in those high-risk situations. This leaves us with a final thought to mull over. Given the extreme stringency and high safety factors required in the performance-based approach, where RSET must be significantly less than an ASET, how much hidden safety margin is truly baked into the deemed-to-comply buildings we inhabit every day? And how reliant are we on the continuous, meticulous vigilance required by fire safety management to ensure we never have to test that hidden margin?